All right. This is the gas stoichiometry notes for advanced chemistry. Um, we're starting on just some examples. We've already talked about all of our gas laws, and so we're going to talk more about how we can use what we've already learned in stoichiometry and combine it with what we know about gases. Now, I have an example that's the explosive decomposition of nitroglycerin may be formulated as follows. So we have our nitroglycerin in a liquid form, which then can be detonated and create 12 moles of carbon dioxide gas, 10 moles of water vapor, 6 moles of nitrogen gas, and a mole of oxygen gas. So what we want to know is what pressure would result from the detonation of 5 grams of nitroglycerin in a sealed 1-liter container, assuming that the resulting gases attain a temperature of 2,457 degrees Celsius. So we have some variables that we need to go ahead and talk about. What are our knowns and unknowns? We want to find the pressure, and we're given 5 grams of nitroglycerin. Okay, so that's a mass. And then we're also given a liter container, which is a volume, and we're given a temperature of 2,457 degrees Celsius, which has to be converted to Kelvin by adding 273. So these would be our variables. Well, we don't have any changes in volumes or changes in pressures or changes in temperatures, so we're not going to use any of the combined gas laws or any of those gas laws. So we are going to end up having to use the ideal gas law. And so to do the ideal gas law, we're going to need some information about um, moles. The key thing here is though we were given a mass of a liquid, which isn't actually about the gases, and we're asking about all the resulting gases. So what we're going to need to do is um, we're going to need moles of gas so that we can use, so we're going to use stoichiometry to calculate this from our grams of liquid nitroglycerin. So we're going to start with just our grams of nitroglycerin, and we're going to convert that into moles first. Okay, to do that, we need to find the GFM of our nitroglycerin. So 3 carbons at 12.01, 5 hydrogens at 1.01, 3 nitrogens at 14.01 if I remember correctly, and then 3 times 3, which will give us 9 oxygens at 16. Once you add all those together, okay, you should get your molar mass. That can convert it into moles. Then we're actually going to do a mole-to-mole ratio, and this is where our stoichiometry comes into play with our information up here in our equation. So we have 4 moles of nitroglycerin for all of these moles of gases, and it is asking about the resulting gases. So since it's asking about the gases, we have to add all these moles of our products together, which would end up with 12 plus 10 plus 6 plus 1, which gives us, I believe, 29 moles. So we'll set up our stoichiometry like this. 5 grams, and when we'll use our molar mass of our nitroglycerin to get to our moles of nitroglycerin, and then we'll go from 4 moles of nitroglycerin to our 29 moles of gases, which is what we want to talk about. After we do that conversion for our stoichiometry, we're going to end up with our value for N. Since we have our value for N now, we're going to be able to use our ideal gas law, which is our PUVNERT. And you can't really see it behind my D, but you guys know it's PUVNERT. And then, so it's PV equals nRT, which gets rearranged to P equals nRT over V. And then we plug in our numbers. Now we're using our R value as latum molk, so we're using 0.0821. That cancels out our liters. That cancels out our let's see if this will work. It does. Okay, it cancels out our liters, our Kelvin, and our moles. And then we end up with our answer as 36 atmospheres. Again, so our answer is in atmospheres. We can only have 2 significant digits because of our 5 grams. All right. So again, we just had to use our molar ratios and our mole to mole ratios um, in order to get to the N value we needed. All right, let's go to the next one. Now, one of the waste products of operation of an ordinary internal combustion engine is nitric oxide. Now, resulting from oxidation of some of the nitrogen that's in the air, the nitric oxide emitted from the engine exhaust is photochemically converted into nitrogen dioxide. Okay, so I want to know what the mass of the nitrogen dioxide would result from the photochemical oxidation of 65 liters of nitric oxide. And this is measured at 27 degrees Celsius and 700 torr. So this NO is my nitric oxide, where I'm actually looking for the mass of my product of nitrogen dioxide. Okay, so all the information that I'm given in the problem, I want to find the mass of NO2. And so, but I'm given information about my reactant of NO. So I've got 65 liters of NO, or nitric oxide. I've got a temperature of 27 degrees Celsius, which then I have to convert to Kelvin. So that's 300. And then I have 700 torr, which needs to be converted to atmospheres. So I can use the constant of Latta-Molch for our R value. So I'm going to divide by 760 torr to get to atmospheres. Okay, so these end up being my variables that I have to work with. All of these, though, right here, my volume, my pressure, and my temperature, are all for nitric oxide. So I'm going to go ahead and use my ideal gas law, or Pevner, first, and find the moles of nitric oxide. Then I'm going to do stoichiometry to get to my mass of nitrogen dioxide. Okay, so with my Pevner, I'm going to rearrange it and find N, so PV divided by RT. All right, then I'll plug in what I know. I know 0.921 atmospheres for every 65 liters. And then I have my R constant, my ideal gas constant in Latta-Molch units. And then I have my Kelvin. So I'm going to cancel out my Kelvin temperatures, and I'm going to cancel out my atmospheres, and I'm going to cancel out my liters, which will leave me in moles of NO. Okay, so when I do that calculation, I have 2.431 moles of NO. And that's, again, we're just going to keep that number in our calculator accordingly. So then after we have our 2.4 moles of NO, we now need to do a mole to mole ratio. So if we go back to our equation, those coefficients in front of NO and NO2 are 2 to 2. So that creates a 2 moles to 2 moles ratio. Then I need to go ahead and find my mass of NO2, which nitrogen would be 14.01 and oxygen would be 16 times 2. So that would give me my molar mass for how many grams per mole there are. So I could use that conversion. So I'll create my dimensional analysis, or my stoichiometry, and I'll take my moles of NO, and I'll set up my mole to mole ratio of a 2 moles to 2 moles. And then I'll use my molar mass of 46 grams for every 1 mole of NO2. Okay, so then we'll multiply and divide accordingly. And we should come up with an answer that's about 110 grams. All right. And that molar mass might have needed to have been 46.01, but I don't think it'll make a ton of difference in your calculations. It might be a little bit off, but yeah. All right. Okay, let's keep moving. So that is actually our information on gas stoichiometry. So you just need to remember that you can get to moles by using your molar mass and things like that, and then set up molar ratios if we have equations and use our gas laws accordingly. So that's how the ideal gas law really ties in, is it allows us to do a lot of that connection of moles into our gas laws. Okay. Now, for the nature of gases or for the nature of liquids and solids, Liquids and solids are more condensed state of matter versus the gases that we've been talking about. Remember, we talk about ideal gases, and most gases actually they don't exist. And in fact, real gases can be condensed or solidified, so those molecules can be pushed together. Liquids and gases will flow, meaning they'll move past one another. I could go ahead and like pour water on the floor and it'll flow to the back of the room. Or I could also spray, an aerosol in the front of the room, and eventually those in the back would smell it. So that would mean that it is flowing. So it's important to understand that both those actually flow and move past one another. Particles of a liquid, though, are held together by weak attractive forces. So again, they more slide past one another versus being broken apart like the gas molecules are. All right. Now, the nature of liquids, we do have a word that we're going to introduce, which is vaporization. And this is the conversion of the liquid to a gas or vapor below its boiling point. So this happens lots of times when you're seeing, like when we wake up in the morning and it actually gets a little bit warmer, then we start to see some of the water vapor start to, the water that's like dew, it'll more become water vapor, but it's not boiling outside. So that's one of those things that it is turning to a gas below the boiling point. Okay. Evaporation is when we have vaporization in an open container that occurs below its boiling point. Evaporation is actually a cooling process in which the highest energy particles, or the hottest ones, escape. And when they escape, they take the heat with them, which then leaves cooler ones behind. Now, evaporation rates increase when things are heated, when liquids are heated. So it is important to realize that that's going to be happening. Now, a vapor pressure is the pressure that's produced in a closed container. So right here, where this closed container is where we have our gases, by the vapor particles, again, our gas particles that are colliding with the walls. Now, as the temperature increases, if I have this sitting on a hot plate, then the vapor pressure also increases, okay? Because this would increase, the pressure would increase more and more and more. And so really most of the time what we see this, if this isn't closed, then this would just escape. And we just see this as more escaping particles. But when we close this and make it a closed system, that causes those particles to collide more often with the side. As they're colliding more often with the side, the pressure increases. Now there's something that we get to that's called dynamic equilibrium. And this is where the rate of evaporation and the rate of the condensation, where they're going to slow back down after they've collided with the wall and transferred their energy, is going to be equal. So the amount of time it takes for them to evaporate, as well as how many of them are actually, the amount of time that it's going to for them to slow back down and become a liquid, which you typically see on the sides of the walls of the container, and then they drip back down, and then they re-vaporize, and then they go back down, and then they re-vaporize. So that's called dynamic equilibrium, when those rates are equal to each other. Now, this is a diagram of it, and so particles will continue to evaporate until they reach a point where they become so concentrated that they literally collide with each other and they reform liquid particles. So this is the rate of evaporation, and then this is the rate of condensation. So it's lower and it increases until those rates are the same. And at this time, the equilibrium vapor pressure is attained. So this is when the vapor pressure is actually attained. And this is when that dynamic equilibrium takes place, is because they're both going to occur at the same time. And it's actually because they're hitting each other so much that they then accumulate on the wall as a liquid and go back down into the liquid container. Now the boiling point. The temperature at which the vapor pressure of the liquid equals the external pressure. So normal boiling points happen at 1 atmosphere. So if we're talking about just the boiling point at 1 atmosphere, then that's typically our normal boiling point. When you go up into the mountains, you have a lower atmosphere, so it actually causes your boiling points to be lower. That's why you actually have high altitude cooking directions on a lot of things, is because those boiling points are lower. When you use a pressure cooker, you put the top on, and this actually creates the boiling point to be higher because you're creating an external pressure on the liquid that is more than normal atmospheric pressure. So that makes it a higher boiling point. And so you can actually cook things faster in a pressure cooker. Now, it is really important that you realize that this red piece right here, this red statement, that once a temperature reaches its boiling point, it never actually exceeds that boiling point. The liquid does it, okay? Now, at that boiling point, it changes into a gas, all right? And so if that's the case, then all of the energy that we're adding to this liquid is going to be to just change it into a gas. So it's just going to be that temperature until all of it is changed states of matter. Once you get it all to a gas, then you could change its temperature. But you can't, but once it reaches its boiling point, it won't change temperature as a liquid anymore. Okay, and if it changes temperature, all the energy that you add to it is going to be there just to um, make it change states of matter. So that's really, really key. All right. Now, this is again just to show that the normal boiling point of substances is the temperature at which a substance boils when the surroundings are at 1 atmosphere. So on this diagram, our vapor pressures over here on the y-axis, it's in torr, so that would be 760 torr. So when our vapor pressures, our temperatures at that particular pressure would be where our boiling points take place, because that is 1 atmosphere. Okay. Now, when we're talking about solids, now the particles in a liquid are relatively free to move around while those in the solid are not. And so the general properties of solids reflect the orderly arrangement and the fixed locations of their particles. And we talked a lot about the forces that hold solids together in our last unit. Okay. When we're talking about solids, though, and liquids, we talk more about the melting point, okay? And that would be that the temperature at which a solid changes into a liquid, or the vapor pressure of the solid and the liquid, are equal to each other, okay? So the vapor pressure of the solid and the liquid are equal, and this is where our melting point takes place. Now, vibrations are strong enough to overcome the attractive forces, so that allows it to become a liquid and start sliding past one another versus being held in that orderly pattern. Now, something you do need to realize is melting point and freezing point happen at the same place, just like boiling point and condensation happen at the same place. Okay? It just depends on whether you're adding energy or taking energy away from the molecule as to what state of matter they become. Okay. Ionic solids have a really high melting point, and that's because of their strong attractive forces that they have. Whereas molecular solids, they have a low melting point, and that's because, if you remember, they have the weaker attractive forces. Okay. So, we see a lot of crystal lattices, and I talked to you about the lattice in the last unit, where we talked about a lot of solids are crystalline, and in that crystal, the atoms or ions or molecules are arranged in an orderly repeating 3D pattern that looks a lot like a lattice work. And I said, if you think about a pie that has that crisscross topping, that's a lattice. Okay. And we talked about unit cells, which were the smallest group of particles within a crystal, which maintain the geometric shape of the crystal. And the unit cells have a regular shape, and we have some crystal systems which can be used to actually identify what solids we're talking about. So some common crystals that we have are a diamond, okay, and then we've talked about and diamonds are those those crystal lattices that we talked about, the network bonding that we talked about in the last unit. And then we have our sodium chloride, which gave us our positives and negatives. So we had our ionic bonding. And then we had our water, which gave us our hydrogen bonding. So this created those crystals when they were in a solid because of that spacing that they create because of their hydrogen bonding, or because of their attraction with their ionic bonding. They're going to solidify into certain shapes. Okay. We talked about the unit cells. You don't need to know a whole bunch about these, but remember we had the simple cube, and then I talked about where if we just put one object in the middle, we got our body centered, but where if we put one in each one of the faces, instead, then we got our face centered. So those were the three that we talked about last unit as well. And so the simple cube would be things like polonium, metal, whereas the body centered would be like uranium metal, and our face centered would be gold. All right. We have a video here that I'm going to play real quickly. Hopefully it'll come through on the video, and we'll go from there. See, I'm going to play it. It may not let me play it while I'm recording. All right. I will try to make sure that I put this. It talks about your cell phone screens and the crystals that make them up, and why it's important for them. So I'll go ahead and try to make sure that I put this video. It should be on the PowerPoint that you can access on Schoology, but we will double check that. Okay. So liquid crystals. Liquid crystals flow like liquids, but at certain temperatures, they actually possess the ordered crystalline structure. Sometimes you guys have seen liquid crystals like in mood rings and things like that. Okay. They actually consist of rod-shaped molecules, which may or may not be in layers. And liquid crystals are what allows like your touch screens to work the way they do and things like that. And they change colors depending on temperature or the electrical charge lots of times. And that's why sometimes you'll see them used a lot in mood rings and things like that. They'll change colors that you can say, ooh, you're attracted to someone right now, or whatever, or you're mad because it's black. And so it just has to do with body temperature, actually. Okay. And I believe that's where I'm going to stop with this recording. I will be able to answer any questions that you have. Feel free to contact me if you need any help.